Hello everyone and welcome back to the channel CSAI Think Tinker Learn. Today we're going to dive deep into the singly linked list architecture and trade-offs. If you're excited to unravel the mechanics of dynamic memory, please hit that like button, share this video, and subscribe to the channel for more content. We'll be conducting a structured analysis of dynamic memory allocation and linear data flow. As you can see, a linked list comprises nodes dynamically allocated and scattered in the memory heap. The head is our entry point leading through data A, data B, data C, and so on until the termination point, indicated by a null reference here. However, there are critical vulnerabilities. If a pointer unplugged occurs, as shown by the broken connection after data C, it results in a linkage failure, causing a critical segmentation fault and leaving downstream unfound orphan data. Attempting to access data D after such a failure will cause a crash, making it a hot zone. This highlights the need for immediate repair for system stability, as noted in Incident Report 404. Also observe that there is no backward traversal capability in a singly linked list, emphasizing its single directional flow. Let's begin by understanding the cost of rigidity, why arrays fail. Arrays are powerful, but they demand a contiguous memory blocks. Imagine a long fixed row of containers. If you need to add a new container in the middle, you can't simply slide it in. You would have to physically move every single container after that point to make some room. This kinetic chain reaction means every index must shift. This operation, insertion, has a cost of O(n), where n is the number of elements that needs to be shifted. For large arrays, this can be incredibly inefficient and slow, limiting their flexibility when it comes to dynamic resizing or frequent insertion. This brings us to the decoupling data from position. The core philosophy of a linked list is to break free from the fixed, contiguous memory requirements of arrays. Let's see, or let's use the coffee shop protocol as an analogy. Instead of fixed seats like an array, imagine people in the queue where each person only knows who is directly in front of them. If someone leaves the line, the entire line doesn't shuffle forward. Attention simply shifts to the next person. This flexibility comes as a trade-off. We lose locality, meaning data isn't physically close in memory, but we gain immense flexibility in managing our data structure. Now, let's examine the component spec or node architecture here. The node is the fundamental building block of our linked list. It has two main parts. First, the payload, which is where our actual data resides in the number 42 here. Second, the navigation or the next pointer, which is the link to the subsequent node. On the right, you see a Python code snippet demonstrating this. A node class with data and next pointer initialized to none. This next pointer is the soul of the machine. If this pointer is none, it means the line ends right there. It's a critical connection that keeps our list together. Next, we delve into the traversal, walking the wire. The time complexity for traversing a single linked list is O(n). This means that to reach a specific node, say the 100th node, you must start from the beginning and sequentially follow the pointers or breadcrumbs one by one. As the caveat states, we have lost the ability to teleport with random access. There is no shortcut. The code snippet, while current equals current.next, perfectly illustrate this linear discovery process, stepping through each node until current becomes null, signify, signifying the end of the list. When it comes to search logic or the linear discovery, singly linked lists have a significant limitation. No binary search allowed. Even if your linked list data is sorted, you cannot perform a binary search because it cannot directly calculate the midpoint address. Unlike an array where you can jump to an index, in a linked list you have to sequentially traverse. This means the worst case search time is O(n), similar to traversing. The caveat here is critical. If your system requires frequent lookups, this is the wrong machine. For such scenarios, other data structures like arrays or hash tables would be far more efficient. Moving on to insertion, the rewire advantage. Prepending an element or inserting at the head of a singly linked list is a highly efficient operation with a time complexity of O(n). To insert a new node before the current head, we first make the new node point to what was previously the head. Then We repoint self.head to the new node. This entire process involves just changing two pointers, making it incredibly fast. There's a critical engineering note here. The order of operation matters. You must connect the new node to the rest of the chain before moving the head pointer. Otherwise, the rest of your list will be lost in memory. Let's analyze insertion latency location matters. Well, the mechanism of insertion itself rewiring two pointer is always fast or O1 instant access. The overall cost can vary depending on where you are inserting. If you are inserting in the middle or at the end of the list, you incur the traversal debt. You first need to find the correct insertion point, which takes O n time. So the total cost becomes find On plus wire O1. In the worst case, this leads to a maximal latency with a total cost of On. This On cost is dominated by the traversal needed to locate the insertion point. Essentially, the bottleneck is not the insertion itself, but finding the insertion point. To address a common performance bottleneck, we have a system upgrade, the tail pointer. The original pain point of inserting at the end of a singly linked list meant a full ON traversal. By introducing and maintaining a tail pointer that always points to the last node, we solve the append bottleneck. The old complexity for appending was ON, but with a tail pointer, the new complexity becomes O1. This upgrade is essential for high performance queue FIFO implementation, where frequent additions to the end of the list are common. It significantly boosts the performance of NQ operations. Now let's talk about deletion, the predecessor prerequisite. To delete a node, say node B, in a singly linked list, we cannot simply delete it directly. We must modify the next pointer of its predecessor, node A, to point directly to node C, effectively bypassing B. This means we must traverse to the k-1th node to perform surgery on the kth node. This highlights a common bug source. If your current pointer is already standing on node B, it is already too late to perform the deletion directly. You need to keep track of the previous node during traversal to successfully execute a deletion. This brings us to the delete last bottleneck. Even with a tail pointer, deleting the very last node in a singly linked list presents a challenge. The tail pointer tells us that where the end is, but not who precedes it. To properly update the tail after deleting the last node, we would need to find the new last node, which means walking all the way from start to node n-1. The operation still has a cost of On. The caveat here is crucial. This limitation is the primary motivation for doubly linked lists, where each node maintains a pointer to its predecessor, making deletion of the last node an O1 operation. Next, let's discuss the soul of the machine, cache locality. While theoretical Bigelow complexity often puts arrays and linked lists on par for certain operations like traversal, both are ON, physics says that the linked list is slower. Arrays benefit from spatial locality, meaning data is stored contiguously in memory. When the CPU accesses one element, it often prefetches nearby elements into its fast cache, resulting in a cache hits and contiguous memory access. Linked lists, however, have scattered addresses, leading to memory fragmentation and frequent cache misses. This means the CPU has to constantly fetch data from slower main memory, which can be 100 to 200 times slower than accessing data from the L1 cache. This is a significant real-world impact on performance. For advanced manipulations, we often employ the two-pointer pattern. This technique involves using two pointers that traverse the linked list at different speed. Use case 1 is cycle detection, where if a fast pointer moving p.next.next and a slow pointer moving p.next ever meet, it indicates an infinite loop or cycle in the list. Use case 2 is finding the midpoint. If the fast pointer reaches the end of the list, the slow pointer will be at the exact middle. The fundamental principle is that since we lack length metadata, we use relative velocity to determine state within the list. Here are the performance specifications for linked list. For traverse and search, The time complexity is O(n) because both require sequential access with no random access. Insert head is an efficient O(1) operation. Insert tail also become O(1) with the tail pointer. Delete head is also highly efficient at O(1). However, delete tail is an O(n) operation because without a backward link, you must traverse from head to find to the second to the last node to update the tail. This highlights the architectural limitation of a singly linked list. Finally, when to use this architecture? You should deploy for singly linked lists in scenarios like stacks, which are LIFO, and queues, which are FIFO, for their efficient push-pop and NQ-DQ operation. These are excellent for undo history and dealing with indeterminate data sizes due to their flexible memory allocation. They thrive in high write, low read environments. Conversely, you should avoid for system needing random access, as arrays are superior here. Also avoid them for fixed data sizes, where arrays are generally faster and for heavy search requirements. In a sense, the singly linked list sacrifices read speed for write flexibility. It is the engine of dynamic growth. Thank you for watching. What are your thoughts on the trade-offs of singly linked list? Share your comments below. Don't forget to like, share, and subscribe, and hit the notification bell for more insights into the fascinating world of computer science. Thanks for watching. Until next video, bye.